Okay, we discussed projectile motion last time. We solved the example using still the same theory, kinematic equations for x and y directions, right? The key is that you break the projectile motion into x and y directions. In x direction, nothing on it, so the acceleration is 0. It's actually the simplest motion, the uniform motion. In y direction, it's still free fall. Okay, so the acceleration is always 9.8 meters per second squared down. Okay, and we know how to work with these two motions, right? Still the same theory, right? You apply the same theory on x and y directions separately. Don't get these numbers mixed up. The only value you can use in both an x and y direction the same is going to be the time. Okay, so we're going to do more practice in this lecture. Okay, so another practice we want to, again, we just want to practice this theory. Okay, we want to do this. Sometimes this is also a very interesting question in projectile motion. Say if a projectile is launched at a certain height, okay, and then with a velocity at an angle, and then, of course, it's going to be moving like this, right? And then say if this projectile is going to land at the same level. So it's pretty much like the question we discussed last time, right? Totally symmetric. The projectile lands at the same level, the same height, okay? So if this is the case, but you can launch this projectile at different angles, right? You can launch it this way, that way. In this case, we want to find the best angle to launch this projectile so that it's going to travel the longest distance in x direction. So again, this is not intuitive at all. This is not intuitive at all, okay? We're going to use this theory, okay, to find the best angle to launch this projectile so it's going to travel the longest distance in the x direction, which is called maximum range, okay, in this question. So this is a classical question in projectile motion, okay. So for example, in a football game, right, if the player kicks a football, of course he's going to land at the same level, right? So in which angle should the football player kick the ball so that it's going to go the largest distance in the horizontal direction? So that's what we want to do here. So let's see. Say again, if I only know the initial velocity, right? If a player kicks the ball, he's going to kick the ball with the same strength, right? But he can pick a different angle, okay? So VI, say we know a variable VI. And we also know a variable theta, the angle theta. So we want to find, again, now we're doing, we want to find a general conclusion. So I'm not going to use any specific numbers. I want to use all these symbols. And then I want to just find a conclusion. And then I look at the conclusion. I use the conclusion to find out which angle is the best angle. Okay, that's what we're doing. So no numbers. So say, okay, it's a player kicked the football, okay, so it's going to land on the same level. If I want to find the maximum distance, right, that's still XF. So let's start with that. If I want to find XF, which equation do I use in the in the x direction? The only useful equation is the second one, right? We have seen that in the last lecture. So if I still call this origin, right, this is origin, so this is xi equals 0, yi equals 0, right? So the xf at this point is what I'm trying to find, right? So I want to find expression for this xf and then see how many variables are in this expression and then how I can make this xf the largest by varying these variables, okay? So that's what we're doing. Now let's start with that equation, right? The only useful equation is going to be the second one. So it's going to be xi plus vxi delta t plus 1/2 ax delta t squared. Now let's see, do I have some information from this problem I can plug in? Xi is 0, Okay? Vxi, I don't know Vxi. I only know Vi and theta. But I know that Vxi is just an x component of this guy, right? So again, if you break this into x and y components, this is going to be Vxi. And of course, this is Vyi. So I can actually write Vxi in terms of Vi and theta, right? I can write an expression for that. So I will replace this with Vi and theta, okay? So that's good. And then, but I don't have delta t. Let's leave it here. And this term is going to be, what is the acceleration in x direction? It's 0, right? Okay, nice. Because nothing's on it. Projectile motion. So you see that I can find an expression for this guy using Vi and theta. So I'm going to keep these two variables there, right? Because these are the variables I can change if someone kicks the football. And so the only thing I'm missing is delta t. But I've already used the only useful equation in x direction, right? Remember, the only useful equation in x direction is the second one. The first one, the third one, if you plug the acceleration 0 in, you just get the final velocity equals the initial velocity, which you already know, right? It's not going to give you anything. So that means I cannot find the time in x direction. But remember, the only thing you can plug in both equations the same, it's going to be the time. So I can find the time in y direction and then plug it back into x direction. So I will get a final expression for xf, which is the horizontal distance traveled. Then I'm going to see how I can make that expression the maximum. Okay, so that's going to be our first step. I'm going to use the y direction to find expression for the total time. Then I'm going to plug it in. So that's going to be the first part. So that's the question I want you to answer on the next slide, slide 13. I want you to use Vi and theta to find expression of the travel time for the ball. So now let's go to y direction. If I go to y direction, I should try the first or the second equation, right? Because only they have the time. This equation doesn't have the time. If I use this equation, let's see. Try the first equation. Vyf equals Vyi plus Ay delta t. In this case, what is Vi? Vi, again, I can find expression for Vi. Okay, using Vi and theta, right? That's just a vector analysis. We have done that. Okay, so that's good. What is Ay in y direction? What is acceleration in y direction? Negative 9.8, if that's a number you want to plug in. Now I just want to use symbols. So I'm going to plug in negative g. Right? I'm not making g negative. I want to plug in the acceleration in y direction. The value is g, or 9.8. But it's down. I want to tell the equations it's an acceleration down. So I will have this, but I don't have the Vyf here, right? At this point, I don't know anything about this point, right? Because again, you need to find the velocity of this football right before it hits the ground, okay? That's the projectile motion, right? When it's hitting the ground, that's another process, even though it's very short, very quick, but that's a different process, okay? We're only looking at the projectile motion, okay? Now in that case, you don't know the velocity at this point, right? You can draw it. I know that it's going to be some in this direction, right? It's going to be tangent. But again, you're going to break this guy Vf into x and y components. But I don't have anything at this point, so that's not going to help us find this time. But remember, in a projectile motion, there's always one special point you can try if you don't know what to do, right? The top. Okay, the top. The top is here, and I know that the velocity in y direction is going to be 0. Okay, in x direction it still has the velocity, right? In x direction, the velocity is always the same. Okay, the velocity doesn't change. So you shouldn't say at the top the velocity is 0. Okay, that's also wrong. You should say the velocity in y direction at the top is 0, because in y direction it's pretty much like a free fall with the initial velocity when it's reached the top, so it cannot go any higher. Now in this case, if I pick this guy as a final, so I'm going to switch my final to this point, then I will have the V final, 0. Then I can plug this equation, plug that number in this equation, rearrange this equation, find delta t. But I only find this time, right? Okay, this is symmetric, right? This top is right at the middle. Again, this is not always true for any projectile motion. You should be careful, okay? As I said last time, a lot of people actually make this mistake. They see a projectile motion, they pick the top, they don't know the time, they just assume it's in the middle. It's not always, unless it's symmetric, okay? If it's symmetric, this half equals this half, right? So this time equals this half. So this is the symmetric projectile motion, right? It starts from this point and then it lands at the same height. The top will be the middle, okay? So that means I can pick the top as the final. If I pick the top as the final, I can use this equation to find half the time, right? Rearrange this equation, the final velocity is 0, initial velocity, you use the expression with VI and theta. Acceleration, plug in negative 9.8, right? But again, this is only the half the time. Once you have done that, remember to double it, you can get the total time. Right? So you will get an expression at the end. Okay, that's the travel time of the ball in the air. So we find the time in y direction. All right, now you can pause the video and see if you can find the expression. Okay, let's see. So first of all, VYI, right? This is how you break it into x and y, right? Right triangle, use this right triangle. So VYI is this side, these two sides are the same. It's going to be hypotenuse times sine. Oh, I'm sorry. Okay, so this is still the initial I pick, right? I'm just picking the middle as a final. I'm not changing the initial. So if I use this equation, final point is going to be 0 because I picked the top as a final. In y direction, velocity 0. This is going to be the expression for VYI, and then plug in negative g, and then that's the time. The half for half of the trip. You rearrange this equation, what do you get? You get half of the time is going to be VI sine theta over g, but that's the half the time, right? The problem says the first thing I want you to find is the total time. You multiply by 2, you get 2 VI sine theta over g. So that's the right answer. Okay, that's the expression for the total travel time of the ball in the air. Now, now let's move on to the second part, which is what we want to find. Don't forget what we're doing. We actually want to find an expression for the distance it travels in horizontal direction, and we're going to take a look at the expression to see how to make it maximum. Okay. Now you see that this is going to be the time you plug in, right? Expression. Just use that expression, put it here, literally. But you still need the expression for Vxi. Vxi you can also find that using Vi and theta, right? You just break it into x and y components, okay? Once you have them, multiply them together, okay? You will get the final expression for the horizontal distance the ball travels, okay? So that's going to be this slide, slide 14. Now you can, again, pause the video, see if you can find the right answer. All right, so what is the expression for Vxi? That's going to be this side, right? So that's adjacent to this theta angle. If you tell me this launch angle, so that's going to be Vi cosine theta in this case, right? Now let's put everything together, right? Vi cosine theta times this, what do you get, right? Okay, so you can put these two VI's together. So at the end you will get 2 VI squared at the top, okay? And then you have a sine theta, cosine theta over G. That's a complete expression for the horizontal distance this projectile travels, right? If it lands at the same height, the same level, okay? Now what we're going to do is this. We're going to make use of an identity, a trig identity, if you still remember that. Even if you don't remember that, that's fine. I'm going to tell you there's identity in trig. 2 sine theta cosine theta, it's always going to be equal to sine 2 theta. So this can be proved. I believe you learned how to prove that, okay? But we're not going to prove this here. So that means, why do I do that? Because, to take a look at this expression. Sine theta and theta, they change differently with the theta angle, right? If you remember that, sine theta actually gets larger if theta angle gets larger, okay? Only between 0 and 90, right? Cosine theta gets smaller when the theta angle gets larger. So if I want to see how these two guys are going to, the product is going to reach the maximum, it's hard for me to see, okay? This guy is going to, when theta goes up, right? Sine theta goes up, but cosine theta goes down. How do I know the product of this guy, which one, at what angle theta is going to reach the maximum, okay? It's not intuitive at all. It's not intuitive at all. So that's why I want to make sure that I only have one variable here. So if I replace 2 sine theta cosine theta with sine 2 theta, what do I get? So this 2 sine theta cosine theta is going to become sine 2 theta. So I will just get vi squared times sine 2 theta at the top, right? So the angle becomes sine 2 theta. So that is my conclusion, okay? So now I'm going to erase all these things. The conclusion is this. So, oh, I don't want to erase this. The horizontal distance travels, okay? It's gonna be, so in this case we call it range, okay? But again, it's just a name, okay? For this horizontal distance travels in this special type of question. This is just xf. We use a big R for that. That's going to be vi squared times sine 2 theta over g. Okay? Now we can figure out when this R, this range, or the horizontal distance is going to travel, it's going to reach the maximum. Say this vi is going to be a constant. If the player kicks the ball, the player doesn't kick the ball the same hard with the same strength, right? So basically he's just going to give the ball the same initial velocity, the same energy. But the angle, he's free to kick the ball at any angle, right? So if this vi is a constant, right, he's always going to give the velocity, the initial velocity of the ball the same. How does this whole thing get the maximum? Well, that means you need to make sure this sine 2 theta reaches the maximum, right? Because g is 9.8. What is the maximum value of a sine function? That's 1, right? Because the sine function can only vary from 0, negative 1 to 1, negative 1 to 1, right? So the maximum value, it's going to be when sine 2 theta equals 1, right? So when does sine angle equal 1? That's when this whole thing equals 90 degrees, right? So you want to make this angle, this 2 theta angle is going to be 90 degrees. So that means theta angle must be 45 degrees. Right? If theta angle is 45 degrees, 2 times theta is 90, you plug 90 in, you get 1. So the maximum range you can get is going to be vi squared times 1 divided by little g. Okay, so that's a very nice conclusion, okay? So if you launch a projectile and then you can launch it at different angles, so what is the best angle you launch it so that it's going to go the largest distance in the horizontal direction? It's going to be 45 degrees, okay? Again, this is not intuitive, okay? Maybe it's intuitive to you, but you can't explain that. Why is it 45 because you just guessed that. But if you use this theory, you do the math, right? You figure it out, well, that's the final expression for this horizontal distance. So this is always true. You plug in any vi and theta, this is going to give you the horizontal distance, the horizontal range it's going to travel. How do you make this value maximum? You're just going to make this sine function maximum. And that's when theta angle equals 45, you get this sine function maximum 1. You plug it in, you will get this. Okay? So that's a very useful conclusion. So a lot of players, okay, their coach is going to tell them, like a football player or basketball player, okay, if you play basketball, okay, the coach is always going to tell you, when you shoot the basketball, you shoot it at almost 45 degrees, okay? They may not know the physics, okay, but they know that from their experience, 45 degrees is the best angle. Why? Because it's going to make the ball, you know, reach the maximum horizontal distance, okay? So that's the reason. But that's the physics behind it, okay? Because you do the math, at the end the math is going to tell you 45 is the best angle if you want to the ball to reach the largest distance in the horizontal direction. So you can take a look at this graph on the slide 15. Okay, so it plots the trajectory of the same projectile with the same initial velocity but different angles. You can see that 45 degrees is definitely going to reach the maximum horizontal distance, right? Any angle larger than 45, it's going to go a little higher, but it's going to be shorter, right? Okay, so another conclusion we can get from this expression is that any complementary values of this angle theta is going to give you the same value of r. What is complementary angles? That means two angles, you add them together, you get 90. So 30 and 60, they are complementary. 75 and then 15 complementary. So you compare their distances, right? 75 and 15. In horizontal direction, the projectile is going to reach the same distance. 60 and 30, okay, they will reach the same distance horizontal, okay? Again, that's because there's an identity in trig sine 190 minus an angle like alpha, it's going to be equal to sine alpha, okay? And then if you divide it by 2, that's what you get, okay? Complementary angles are going to give you the same horizontal distance in x direction. Okay. So another question I usually get in this part is that, do I need to memorize these conclusions? Do I need to memorize these two equations? So you may ask me to plug numbers in. No, you don't. You never need to memorize special conclusions, special shortcuts, so that you just expect that on the test you get a question, you remember this expression, you write it down, you plug numbers in, you get the answer. That is not physics. What we are learning is this. How do you derive this using the theory we learned for projectile motion? Okay, once you have derived this, you can figure out how to make this range maximum. Okay, that's what we're learning. That's what you, if I give you a question like this, I would want you to show me how to derive that. I don't want you to show me that I remembered this expression. I'm just going to write it down, plug numbers in, and get the answer. That is not physics. That is not what we're learning in physics. Okay? You should be able, you should know how to start with the fundamental theory to derive anything you need for a specific type of question, okay? The conclusions are going to be different for different types of questions, but the theory is the same. That is what we are learning in physics, okay? We're not learning how to memorize these special conclusions for different types of questions. That's not what we do in physics. Now let's take a look at an example, okay? So we can practice this conclusion, okay? So say I have already derived this conclusion. I want to use this conclusion, okay? So I can use this conclusion to solve some symmetric projectile motion problems. If I'm interested in the largest maximum horizontal distance, horizontal range. Okay, so take a look at the question in slide 16. You are in a soccer game and want to pass a ball to a teammate who is 9 meters away from you. Okay, you remember that in Physics 113 you learned that a projectile shot at an angle of 45 degrees to the horizontal will reach the maximum horizontal range. Hope you still remember this after you finish this class. You then kick the ball at about 45 degrees. Okay, so of course it's going to go the maximum horizontal range. Okay, but it comes too strong. Okay, comes too strong and reaches the opponent 12 meters away from you. Okay, so it turns out that you don't need it to go the maximum horizontal distance, right? Because the maximum is going to be 12 meters. You only want it to go 9 meters. Estimate the correct angle at which the ball should have been kicked. Okay, so let's see how I can find that using this conclusion we drew. Okay, but again, as I said, you don't need to memorize this. You don't. Okay, you need to know how to derive that. Say I have already derived that. Now I can go ahead and use this conclusion. So I know that the maximum range is going to be 12 meters from the question, right? Because when I kick the ball at 45 degrees, it's going to go 12 meters. But I don't want that. I want the distance to be 9 meters, right? So that's going to be the XF. I want it only travel 9 meters. So what is the angle I should kick the ball if I only want it to travel 9 meters? Now let's use this conclusion we just derived. So that means I will do 9 meters equals VI squared sine 2 theta divided by G, right? So I can rearrange this equation to find theta if I have the numbers I need, okay? Little g, that's 9.8. When you see little g, that's just 9.8, right? Little g is just a name for 9.8. It's like pi is a name for 3.1415. But you are missing VI squared, okay? That's when you use this information to find VI squared, right? You're missing something, okay? That means you need to use some other information in this story to find that thing before you use that and this final equation to find the theta angle you need, okay? So that means you don't do that in one step. You may need to do it in 2, 3, 4, 5 steps. Now, let's see. How do I use this equation, the information, to find this VI squared? Well, I know that this R maximum value is always going to be VI squared times 2 times 45 degrees, right, divided by G. Now you see that you can, because 9.8 is here, 12 meters here, you already know the maximum range. You just rearrange this equation, you will find VI, or VI squared, right? And then you plug it in, you will find the correct angle the ball should have been kicked in order to reach your teammate. Okay, so 2 steps, but the same conclusion. Okay, now you can pause the video, find the angle. All right. Okay, so let's see. If I want to find VI squared, that's actually very easy because it's just going to be, you rearrange this equation, what do you get? You just get it's going to be 12 meters times little g, right? Because this is going to give you 1. And then you don't need to plug in this little g, okay? You can actually put it here, because what do you get? You will get 9 meters equals VI squared, which is 12 meters times little g, right? And then sine 2 theta divided by little g. Now you see that little g and little g cancel, right? So you will get 9 meters over 12 meters equals sine 2 theta. Now you can take inverse on each side, right? So 2 theta is going to be almost 48 degrees. And the theta angle is going to be almost 24 degrees. All right. So the correct angle you should kick the ball, it's gonna be 24 degrees. Okay. That's how we make use of this conclusion. But again, you should be careful. This is not true for any projectile motion, right? This is only true. This is a very special case we discussed. Again, we use this case to practice the theory. Okay. We're just doing practice. Okay. We're just practicing the same theory, right? How do you get used to? How do you be good at something? Practice. Okay. It's always practice. Okay. Now the next thing we want to do again is another practice on projectile motion. This is also a classical problem in this part. This is a thought experiment. It's called the monkey and the hunter experiment. So take a look at the slide 17. Okay. So this is a very interesting experiment. It's a thought experiment. Okay. We don't do that in real life. Okay. The experiment is this. Say if there's a hunter, okay, carries a blowgun, okay. The hunter goes out to the woods, okay, trying to hunt for some monkeys, okay. And then the hunter sees a monkey hanging in a tree, okay. Of course, this hunter is going to aim the gun at the monkey and open fire, okay. So the experiment is this. The monkey, at the same time, the monkey also sees the hunter. Of course, the monkey doesn't want to die, right? So what the monkey does is this. As soon as the hunter opens fire, the monkey is going to let go of the branch, so it's going to just drop, right, straight down, okay? Drop straight down. The question is this, okay? In this case, is the bullet going to hit the monkey, right? The monkey is going to die or not, okay? In this case, okay? So that's a thought experiment. So we never really do that in physics, okay? How do we figure that out? So let's first draw it out, okay? Let's first draw it out. So that's the gun. So the hunter opens fire, so the bullet is just gonna go this way, right? So the bullet goes this way, but excuse me, the monkey is gonna drop at the same time straight down, right? So so I'm just gonna draw the bullet, okay? The bullet goes that way. But remember, the bullet has gravity, right? So the bullet is not going to go in a straight line. The bullet doesn't go in a straight line. The bullet is actually going to be in a projectile motion. It's going to be in projectile motion, right? So the bullet is pretty much like you throw something with an angle like this, right? So it's going to go actually this way. So the monkey is falling straight down. So if I ask you, is the bullet going to kill the monkey or not? Well, it might, okay? Because the bullet is going in a parabola and the monkey is going straight down. Well, if the bullet is going in a straight line, of course it's going to miss the monkey, right? Because the monkey has already left the branch. So if the bullet goes straight line, no, it's not going to get the monkey. But the bullet also has gravity, so it's not going to go straight line, it's going to go this way. So how do I decide, how do I figure out if the bullet is going to get the monkey? Again, you don't do things intuitively. I want you to give me a definite answer. Is the monkey going to be killed or not? I want you to give me a 100% answer, right? You can't tell me, well, looks like it may kill the monkey. It may not kill the monkey, okay? I'm not sure, I can only bet. That's all what we do in physics, right? In physics, we always want to make a numerical prediction, a very precise prediction. We don't want to guess, we don't want to bet. We want to make a very precise prediction. So how do we make that prediction in this case? So that's how we do that, mathematically. I'm going to calculate the position of the bullet when it has reached this vertical line, right? So in order to kill the monkey, the bullet at least has to travel this horizontal distance to reach this vertical line, right? And then I'm going to calculate the horizontal, the vertical height of this bullet, say Y bullet. I will get a number, okay? Then I'm going to do the same analysis with the monkey. So the monkey starts to fall as soon as this the hunter opens fire. So the monkey is going to start to fall. So I'm going to calculate the position of the monkey right after the bullet has reached this vertical line. I'm going to calculate this number for the monkey. Then I have these two heights. I have the location of the bullet here on this vertical line. I have the location of the monkey at this line. I will just compare these two numbers, right? If they are the same height, if the bullet, when the bullet reaches this vertical line, the monkey is also going to reach that point, then the monkey is going to die, right? If I get two numbers like 5 and 7, that means the bullet is going to miss the monkey. So that's how I answer this question mathematically, okay? That's how I make a very precise prediction, right? So, okay, so we're going to use some numbers, okay, in this problem, even though we can draw a general conclusion, but now I want to just use some numbers, okay, some random numbers, so see if I can get a precise prediction, okay? So, and it doesn't have to be bullet and monkey, right? So you can just say this is a projectile, this is a target. A target starts to fall as soon as this projectile is launched, okay? So let's see, if I assume, so take a look at the image on slide 18. So that's how we model this story. So a projectile is just going to be launched from a launcher, and then a target is going to start to fall. So let's assume this is horizontal distance, it's 8 meters, and this vertical height of this target is 5 meters. So we're going to use these two numbers to figure out these two Y values, okay, and see if they meet on this vertical line. So first of all, I want you to do this. So the projectile is still aimed at this target initially, and then opens fire, okay? So initially it's still aimed at this projectile. I want you to find the launch angle for this projectile. Okay, so that's easy, just do trick, right? Because there's already a right triangle here. If you want to aim, if you want this gun, this launcher to aim at this target, what is the angle of this launcher with respect to this horizontal direction? You can just literally use this right triangle to find the angle, right? So that's the question I want you to answer first. Okay, we break it into steps. That's question on the slide 18. Okay, so what is your answer? What is the angle you found? So if I want to find this angle, I can just use tangent inverse. It's going to be opposite over hypotenuse, right? If these are the two numbers I'm given. So this is 32 degrees, okay? So that means if the gun is going to aim at the target, it's going to pick an angle 32 degrees to aim at the target. Now we're going to find this Y bullet. So the position of the bullet, okay, when it has reached this vertical line, okay? So in order to do that, I need the time first, right? I definitely need this travel time so that I can find the Y value. To find the time, it's easier to do that in X direction, okay? So because X direction is uniform motion, and that's only one equation you would choose, right? You don't need to worry about 3 equations, which one do you pick? The only useful equation is going to be the second one, okay? So I'm going to find the travel time for the bullet when it reaches the vertical line, okay, in order to meet this monkey, the target. So I would pick the second equation for the bullet. All right, so if I use this equation, okay, again, I can say this is the origin, this is xi equals 0, yi equals 0, right? So I would have yi here, xi equals 0 here. What is the xf at this point? Well, that's just going to be 8 meters, right? Because that's a distance, horizontal distance it's going to travel if it wants to reach this vertical line, okay? Now what is Vxi? That's when you use this angle and the Vi to find it, right? Because Vi, the problem says Vi is 20 meters per second square, or 20 meters per second. How do you find Vxi? You break that into x and y components, right? This is Vxi, this is Vyi. That's why we want to find this angle 32 degrees in the first part, right? If you have Vi and theta angle, you can definitely break it into x and y components, right? You use sine and cosine. So that's how you find Vxi. Now delta t, I'm going to leave it here because delta t is what I want to find. What is the acceleration in the x direction if the bullet is in a projectile motion? 0, right? Now you see that once you find the expression for Vxi, you can rearrange this equation, find the time. Okay, now you can pause the video, find the time. All right, so let's see. If you use this triangle, right, break it into x and y, what is Vxi? Vxi obviously is going to be Vi cosine theta angle, right? Vi is given, theta angle what we found in the first part. So this number I found is 16.96 meters per second. So that's the velocity in x direction, the initial velocity in x direction of the bullet. And it's going to be the same velocity all the way, right? X direction, that's uniform motion. Okay, so you can rearrange this equation. You can find delta t. It's going to be 0.47 seconds. Did you find the right answer? That's what I found. Okay, so I have found this. Now let's move on to the next part. Now I can find the y bullet, right? How do you find the y bullet? Let's pick an equation here. That's going to be the final position of the bullet, right? If I call this initial. So it's going to be either the second one or the third one. Let's pick the second one, because the second one already have YF on the left hand side, right? So for the bullet, okay, so let's see, this is a bullet or the projectile. YF is going to be YI, that's YI. So what is YI? Well, I picked this as my origin, so that's 0. Plus VYI delta t. Okay, so VYI, you're going to still find it using VI and theta, right? Because you just break VI into x and y. Delta t, okay, we found it. So that's what the time you plug in. Okay. Now 1/2. What is the acceleration in y direction? Negative 9.8. Now I'm using numbers, right? Because I want to find the number. I don't just want an expression. And delta t is squared. Okay, now you see that delta t we found. All you need to do is just use VI and theta to find VYI and then plug it in. Okay, then you can find this number. Okay, so pause the video, do the algebra, and compare your answer with mine. So this VI, it's going to be VI or VYI. It's going to be this side, which is this side, so it's opposite to this theta angle we found, right? So that's going to be sine theta. So this number I found is 10.60 meters per second. Now you can plug all the numbers into this equation we just picked. What is this number? This number I found is 3.9 meters. So that's for the bullet, okay? Now we can move on to the last part, okay? let's find the YF of the monkey. The monkey is already on this vertical line, but I just want to find where the monkey is when the bullet has reached this vertical line, right? So I can compare these two numbers to see if the bullet is going to meet with the monkey, then the monkey is going to die, right? So now let's still try the second equation, right? Because I already have the YF on the left hand side. What is the YI of the monkey? Now that's not going to be 0, right? The monkey starts from this, from the tree. So the YI is going to be the height of this target, 5 meters. What is the initial velocity of the monkey? Okay, the monkey lets go of the branch, so the monkey just drops from rest, right? So that's going to be 0. So the second term is going to be 0. Now the third term, 1/2. What is the acceleration of the monkey? The monkey is in free fall, okay, negative 9.8 t squared. What is the time you plug in? Well, okay, in this thought experiment, we assume that the monkey starts to fall as soon as the hunter opens fire. So this time is going to be this falling time, right, of the monkey. So you're going to plug in the same time, okay? Now you see that the only thing you need is going to be the time. So what is now you can plug all the numbers in, find this Y position of the monkey. So the number I got, it's going to be 3.9 meters. So that means, compare these two numbers. After 0.47 seconds, this bullet is going to reach this vertical line, and it's going to be at a position 3.9 meters above the ground. After 0.47 seconds, this monkey has fallen to a point which is 3.9 meters above the ground. Okay? The bullet is going to meet with the monkey. It's going to kill the monkey. Okay? So, and then you see that we picked the two random numbers. So it doesn't matter what numbers you pick, this and that. Okay? You will, and the initial velocity of the projectile, you will always get these two heights. The height of the monkey or the target, the height of the projectile or the bullet, the same. So if you want to prove it, okay, as a general conclusion, you don't use these numbers. You're going to call this a variable. You call that a variable. You call this a variable. You plug all the symbols in. You will get two expressions, like this YF and this Y. The expressions are going to be the same. Okay, so this is going to be general conclusion. So for this thought experiment, the monkey and the hunter experiment, if the hunter aims at the monkey, okay, and opens fire, at the same time the monkey starts to fall straight down, okay, the bullet is always going to get the monkey. So the monkey is always going to die, okay? So that's a thought experiment. But we do have we can set up experiment, okay? We can set up this experiment in this classroom to do that. Of course, we're not going to catch a monkey and shoot it, right? As I said, all you need to do, just use a launcher to launch a projectile and then set a target here. But make sure you have a mechanism to release this target as soon as this projectile is launched, okay? So that's what we're going to do next. I'm going to show you this experiment, okay?